So this is the electric force. But in physics, they're not interested in the electric force. They're interested in the force per unit charge. So what they do is they come in, they take this vector field. This is a vector field, isn't it? There's a vector in here. Okay. These are all numbers, aren't they? Number, Q is a charge. It's going to be a number. Capital Q is a charge. That's a number. This is the magnitude of a vector. That's a number. So this is all a number times a vector. So that's a vector. It's a vector field. If we define a new vector field, capital E of x, to be equal to that field divided by Q, then what would happen if I take this field and divide it by Q? Little q. Little q's cancel, right? And I just get E epsilon Q over x, magnitude of x, times the vector x. Okay? And this is your force per unit charge. Or, yeah, force per unit charge. I'll put it here. Force per unit charge. And this is something that will always hold for any charge that you put at the origin, and then you place another charge out here relative to it. This has a position, right? The position of this is x, y, z. Then the force per unit charge is some measurement of what's happening between these two, right? Got it? How these two charges are interacting with each other. All right, what do I want to do now? I want to get to the problem. This is the big thing we're going to work with right here. I want us to show that the flux of E with respect to S, okay, so this surface flux is equal to 4 pi epsilon times Q. Does that all look familiar? I don't know. Maybe you've seen that. Maybe. That this is equal to that for any S which encloses the origin. That's it. That's what we want to show. So if I put a charge here, if I put charge Q at the center here, have another charge here, then the force per unit charge along a surface, right? You have this surface. Imagine any three-dimensional surface, right? That encloses the origin. So it encloses our charge, right? That will always be this right here, which means it's always a constant, but it depends on the charge that you started with. Okay, so you change this charge, this is going to get bigger or smaller depending on Q. We want to show that holds for any surface that encloses the origin. Now, we ran into a problem like this a while back. I showed you this example where we were trying to show something for any circle or any curve that enclosed the origin. Do you all remember that? And we were able to do it. We were kind of sneaky about it, but we did it. I'm going to do something similar here. All right, so the first thing I'm going to do, here's my picture. I want us to call this surface right here, just to make it easy to go back and look at what we drew a second ago. Let's call this right here S2. All right? So this surface that encloses our origin point, this is S2. I would like for us to consider S1 So this is my solution. Consider the surface S1, which is going to be a sphere of radius A, which is inside S2. So do you agree that if somebody gives me a surface that encloses the origin but does not actually touch the origin, that I can always find a small enough sphere to fit inside of S2? You agree with that? You have to agree with that. Yeah. You're okay with it? Okay. So this inside of here, it might be really small, but I should be able to control I pick a radius which is going to make it small enough to fit inside. So here I go. Here's my sphere sitting inside. That's S1. You still with me? Yeah? All right. This looks a lot like the donut, right? That we did a second ago? What can you tell me in terms of what we did before? If E is the solid between them, be very careful there, solid between them. Please put it away. Okay. If the E is the solid between them, which is the bread part, right? Then what can we say? I wrote down a thing here a second ago. Yes, it's the triple integral over E of the div of F, right? dV. Our field here that I want to be working with is E, okay? Don't confuse these two E's. F was the force field, but I said let's define E to be the the force per unit charge. So do you agree that our new field out here is the field E, not to be confused with the solid inside, which is just E without a vector? Should I change the name of the solid, or are y'all okay? Okay. All right, so this should be equal to what? The surface integral over S2 of E dot ds. It's still with respect to surface area, so ds. Then what? Minus surface integral over S1 of E ds. We still good? Now, if you remember how I snuck in and did the other problem, I was able to show one of these with something real quickly and easily. I'm going to do something similar here. I'm actually going to work on the left side of this right now, which means I want to find the div of E. All right? What's going to happen is that this is actually going to become 0. And because it's 0, that means that these two, when I move this one to the other side, must be the same. And if these two are the same, that means to find this flux over S2 is equivalent to finding this flux over S1. And I can do that because I have a nice, good definition of what S1 is, right? But I still have to show that the div of E is 0. So that's what we get to do now. So I'm going to say here now, but the div of E equals, well, what is E? Div of, it's a vector, isn't it? Tell me what E was. It was epsilon q over magnitude of x cubed times x, right? That was it. But what is x? What is this x vector? Maybe we never stated that from the beginning. The x vector is the vector that goes from the origin to little q, which is just the point xyz, which is the vector xyz. So I want you to convert this now to say this. E, or epsilon times q over what is the magnitude? What is the magnitude of x? Square root of x squared plus y squared plus z squared, all of this cubed, right? Times x, y, z. Right? This is a constant. I multiply it through. So this becomes, sorry, I forgot to put my div in here. I haven't taken the div, have I? No. I'm taking the div of this. I'm taking the div of this. I'm going to do that as I work through here. So I need to do the div of, as a vector, it's x times this, right? So EQX over root x squared plus, it's about to be junk. Give me just a second. And then here, E epsilon Q y over square root of x squared plus y squared plus z squared. And then epsilon Q z over square root of x squared plus y squared plus z squared. I need the div of that. So maybe we can do what we did a second ago. We can just look at one of them and see the pattern in the derivative and just do the same for the rest. Okay, what is the partial with respect to x of epsilon qx over root x squared plus y squared plus z squared? All right, quotient rule. Derivative of the top with respect to x, epsilon q times the bottom. I'm going to go root junk, right? Root j. Minus the top, epsilon q x times the derivative of the bottom, which is 1 over root junk. Yeah, you're going faster. 1 over 2 root junk times the derivative of what's in there, 2x. And that's it for the top, right? All of this divided by root junk squared. So just junk. We still good? 2's cancel. See if. We did. Hold on. This is bad. This is bad. No, we didn't forget. I forgot. Yes. Yeah, do y'all see that? Look, when we distribute this cube, y'all let me forget this. You did on purpose. Look, I'm going to rewrite this to the 3 halves. Is that all right? 3 halves. That's going to change some things here, isn't it? 3 halves. We got to start this over. I think the top, this is the same, but it's not root junk, it's junk to the 3 halves. This is the same. Yeah, I'll get to that. Let's do this part right here. Okay. We all right there? All right, well, derivative of this is 3 halves the junk to the power came down, so 1/2 times 2x. All over. This, when we square it, the root goes away, so you just get j cubed, junk cubed. It's a lot of junk. I'll try and clean that up over here. Everything has, well, Well, do we want to clean it up or do we want to leave it? I mean, it's kind of up to you at this point. Can I just leave it? Yeah. I just leave it. So if I go to do the div, I'm going to have this expression, again, added to this with a y squared. These twos will cancel. I'll get an x squared here. I'm going to have a y squared on the next one, and the last one will have a z squared, and that's the only difference between them, right? So my div f, or my div e, is going to turn out to be epsilon q junk to the 3/2 over junk cubed. I'm splitting this up into two fractions, okay? Then I have minus epsilon q x squared junk to the 1/2 over junk cubed. You all seeing what I'm doing here? 3 epsilon. And then repeat that, right, 2 more times. So plus epsilon q junk to the 3/2 over junk cubed minus epsilon q 3 epsilon q y squared junk to the 1/2 over junk cubed. One more time. Epsilon q junk to the 3/2 over junk cubed minus 3 epsilon q z squared junk to the 1/2 over junk cubed. Those are all the same. So I have 3 of those, right? Okay, so I have 3 epsilon q junk to the 3/2 over junk cubed minus, now these all have a minus, right? All have a minus, so how can I write that? Minus 3 e q j to the 1/2 over j cubed. That's what they all have in common, right? This one, and this one. So I'm factoring that out of those 3, and what's left over here? I will in a second. I will. What's left here? The x squared plus y squared plus z squared, right? X squared plus y squared plus z squared. But what's x squared plus y squared plus z squared? No, you're at the last problem. That was junk, wasn't it? That was junk? That was the junk.
Are we going to do spherical anyway?
No, we're not. This is going to be 0.
Oh, too bad.
3, yeah, too bad, right? 3 junk to the 3/2 over junk cubed minus 3 epsilon q junk to the 1/2 over junk cubed. But this right here you said was just junk, right? And then junk to the 1/2 times junk, add the exponents, you get junk to the 3/2. And then they're identical. 0. Right? So div is 0, which means that the left side of that equation I wrote earlier is 0. Okay. Not done yet. Therefore, triple integral over e of div e dv being equal to the surface integral over S2 of e dot ds minus surface integral over S1 of e dot ds is actually 0 equals this, right? Which means that they're equal. Are we done? What do I have to do? I actually have to figure out one of these, right? This is the one I'm interested in, right? This is the one that I want to know. This is the one that I created to make this problem work. The S1 was that sphere with radius A. Yeah? Okay, so I'm now going to go after this one right here. I'm going to see if I can do this surface integral. All right? Now watch how I'm going to do this. We could come up with some parameterization of the sphere and all that stuff, but I'm going to do something even more clever, I guess. I'm going to try and use this one right here. I'm going to try and use this formula. Because I think I know something about the normal vectors on a sphere. If you give me a sphere, and here's the origin, if you pick any point out there, of course that point has the coordinates x, y, z, but the vector that goes there from the origin to that point is parallel to the normal vector at that point, isn't it? It points in the same direction. It just doesn't have a unit length, right? So if I wanted to come up with the normal vector, which would be sticking out of here like that with unit length, I would take this vector and divide it by its own length, right? Right, that's what I would do. All right, so I'm going to write this up here. This is equal to this. What is E? We wrote that, we had that down a second ago. By the way, this is D. Sorry. In the formula, because I went from S, right? Since I did the normal in there, this becomes D. D is the domain of the parameters that draw S. What was E? Epsilon Q over magnitude of x cubed times the vector x, right? That was E. I want to dot that with this right here, right? And look at this. Isn't this just x over magnitude of x? Isn't that what that is? Dot that with x over magnitude of x ds. What is a vector dotted with itself? It's magnitude squared. Go back. This is chapter 10, way back in the day. All right, this is double integral over d of EQ of what? Magnitude of x cubed times these two together is magnitude of x squared over this is magnitude of x, then ds, and what is that? Because there's 4 of them down here, 2 of them up there, cancel out, get this? All right, all of this said, what can you tell me about the magnitude of any vector on this sphere? Close, not 1. I chose the sphere. It's A, right? Isn't the magnitude of, if I, remember how we chose this guy, S1? Well, I erased S1 a long time ago, but, right? This was a sphere of radius A. So if I take any point on that sphere, it has a distance of magnitude of A. So I can replace this down here with A squared. So here's where I am now. This is equal to double integral over d of EQ over A squared ds. And if you recognize now, let me check something here. No, we're good. I mean, we're good. Isn't everything here constant? which is the surface area of my surface, which is the surface area of this sphere. The surface area of a sphere is 4 pi r squared, right? 4 pi r squared. This has a radius of a. What's the question? Or no? You good? Would you agree that this has an area of 4 pi a squared because the way I chose it? So this becomes EQ a squared times 4 pi a squared. Cancel, and you get 4 pi epsilon q, which is what we wanted to show. Check. Yes. So I think a lot of times in like a physics class, what will happen is they'll give you a formula, and you just know that they just tell you, like, that's it, right? Like if you ever are trying to find the charge, the force per unit charge, if your surface encloses the origin, it's a closed surface, then you just need to know what the charge at the center was. Take that, multiply it times the constant, which has to do with the units you're in, multiply by 4 pi, you're done. This was to show you where that formula comes from, and they all come from something, right? All these formulas come from some mathematics, and I wanted to illustrate how the divergence theorem is used to generate a formula like that. Okay, I have one more handout. This is your guide to the final. Even if you have one, just pass these around. All right, so can we talk about this? I have 5 minutes. That took me a lot longer than I thought it was going to take me. I'm just going to start by saying that I really do appreciate that a majority of you, a strong majority of you, really did put a lot of time and effort into these take-home exams. You know, when I started this class off in the very beginning of the semester, I told you, you know, these take-home exams are going to require that you put a lot of effort into them. So I do appreciate all the time that you put into it. I hope that you learned a little bit about yourself and your abilities, and just that it was a good experience. I know that they could be a little painful there, but I hope that it turns you into a better student, or it helped do that. As far as the final, these are the topics, and let me just go through each one of these and kind of explain in a little more detail what I'm looking for here. We never tested over Lagrange, but there were all these different types of Lagrange multiplier problems. I promise you I'm going to give you a function of 3 variables with 1 constraint. So you can focus your attention mostly on that. You're not going to have a 2-constraint problem. And I'm going to try and keep it pretty simple as far as the algebra that's going to be required for you to find your lambda and your x and your y and your z. I'm not going to have some crazy algebra that you've never seen before, all right? Just look at your homework problems for that section. 12.2, specifically, there was a section in the homework where you were given a double integral, like they wrote it out. Double integral, gave you limits of integration, they gave you the integrand. And they specifically told you to change the order of integration, which requires you to go and draw the region and then switch it from being a function of x to a function of y, or back, you know, the other way around. So it's in there. It's towards the end of the homework section, or homework problems for that one. For 12.3 through 12.7, triple integrals in cylindrical, polar, and spherical. There's a lot of information in those sections, but you can see from the problems that we did today, we had to do cylindrical coordinates, we had to do spherical coordinates. So that's the type of thing you need to know how to do. I'm not going to go back and pull like specific problems necessarily from those sections. You need to know when to employ those methods in an integral. 12.8, that was change of variables, and those problems could be kind of long. This is going to be kind of a plug and chug problem. I'm going to give you a transformation, and I'm going to ask you for the Jacobian determinant. That's it. Which means you need to know the Jacobian determinant. And what I'm allowing you to have on the test, I haven't told you yet, right? So let me get to the end. 13.2, line integrals along scalar functions and vector fields. So you need to know how to compute line integrals over scalar functions, but then you need to do it over vector fields, which is work, right? That's what work is. Most likely, those line integrals will not be on closed curves, right? Because then you might employ Green's theorem, or the fundamental, well, 13.3 is fundamental theorem of line integrals. You need to be able to find a potential function. Okay, so I'll give you a problem. I'll say, hey, find the line integral over this vector field, and you can do it easy way or hard way, right? Easy way is to find the potential function, plug in the two endpoints, be done, right? Green's theorem, I think that one's going to really like stick out when you see it because it'll be two-dimensional. It'll be a closed curve, and you'll be asked to try and evaluate it, line integral. So you'd use Green's theorem. Green's theorem is in your packet of formulas, isn't it? That big packet of things that I handed you, I'm going to let you have that on the test. Okay, 13.7, surface integrals. There's a lot in this section. If I give you a picture of the surface, you need to be able to find parametric representations of the surfaces. Very similar to the handout that I gave you. Remember that handout? Okay. You need to be able to find the surface area. So I give you a surface, a scalar function, and you find its surface area. Or even if I give you the vector function. You need to be able to do flux. The last two, Stokes' theorem and divergence theorem. Stokes's, you'll kind of know when to use that because you're going to have a surface. You're going to be trying to do a surface integral, and there will be a curve going around it, or the other way around. There will be a curve going around a surface, and you decide which way you want to go with that. So that's the most recent information, right? That was the homework from last time, which hopefully you did, but I mean, no one had seen me do the cube problem yet, so. Divergence theorem, 13.9, that's today's stuff. So, what do y'all think? Y'all worried about it? How do you feel? A little bit? Yes.
Can we still make our own review sheet?
Yeah, this is what I'm going to let you do. I'm going to let you use one 8.5 by 11 sheet of paper, both sides. You may write steps, procedures, formulas, reminders, hieroglyphic shit that I don't understand, but you understand. I don't care what it is. You just cannot have any worked out problems. So if you're kind of like, well, I don't know if he'll let me have this, then don't put it on there. Because what I'll do is I'll walk around, and if there's something on there that gives you an unfair advantage over someone else, then I'll just take the whole thing away, and then you won't have it at all. So if there's any